When you think about math, what comes to mind? Probably this idea of a perfect, unchanging system, right? Like a giant monument of absolute truth. But what if that's not the whole story? What if math is actually more like a living language? Something that's constantly evolving to help us make sense of a really complex world.
And that's really the big question we're diving into today. For centuries, the dream was to build this perfect system, a mathematical fortress so solid and logical that every single true statement could be proven and every false one tossed out. Simple, right? Well, as we're about to see, reality had other ideas.
So our story really kicks off with this incredible ambition, this dream of absolute certainty. We're talking about the turn of the 20th century, and mathematicians were on a quest to put all of math, the whole shebang, on one single, unshakable foundation. And the tool they chose for this massive job? Something called set theory.
Now, the beautiful thing about classic set theory is its simplicity. There are absolutely no gray areas. An object, doesn't matter if it's a number, a cat, a planet, is either in a set or it's out of it. End of story. It's totally binary. You're either a 0 or a 1. And this black and white logic, this was supposed to be the bedrock, the solid ground for everything else in math.
And the way it works is super intuitive. Just imagine these sets are like splotches of ink on a page. The union of two sets is just everything the ink touches, all of it combined. And the intersection? That's just the part where the two colors overlap. Simple, right? It felt like this system was powerful enough to describe, well, anything. But this perfect world of crisp, clean lines was about to run headfirst into a very messy, very human problem.
Okay, so the first big crack in this dream of certainty, it didn't come from some super abstract, high-level paradox. Nope, it came from something much simpler, trying to use this rigid black and white logic to describe the world we actually live in. A world that's messy and imprecise and, well, full of vagueness.
I mean, seriously, think about it for a second. How would you tell a computer what warm means using just yes or no, or young, or heavy? Classic set theory forces you to draw a hard line. You're either young or you're not. This water is either hot or it's not. But that's just not how we experience the world, is it? There isn't one single birthday where you magically stop being young. This kind of vagueness is totally natural for us, but for a system that only speaks in zeros and ones, it's an absolute nightmare.
So clearly, a new idea was needed, and that idea was called fuzzy set theory. Instead of a hard in or out, fuzzy sets introduced this really cool concept of a degree of membership. So something can be partially in a set. You could be, say, 0.8 young, or a cup of coffee could be 0.6 warm. All of a sudden, you've got a system that can handle nuance and shades of gray.
And this visual right here is a perfect way to see it. Just look at that top graph for age. The line for young doesn't just fall off a cliff at a certain birthday. No, it slopes down gradually, while the line for not young starts to climb. What this does is it lets a computer understand something we know intuitively, that a 19-year-old is more young than a 25-year-old without having to make a ridiculous absolute judgment call on one of them.
And hey, this is not just some philosophical game. Fuzzy logic is the real deal. It's the engine powering countless systems you probably use every day. It's what helps your washing machine figure out just the right cycle. It's used in medical diagnosis. And, maybe most importantly, it's how we translate our wonderfully messy human way of thinking into a language that a computer can finally understand.
Okay, so if fuzzy logic was a crack in that perfect foundation, what we're about to talk about next, well, this was a full-blown earthquake. This is the story of a single, simple sentence that completely shook mathematics to its core by revealing a fundamental, unavoidable limit to what logic itself can ever do.
So picture this. The year is 1931. There's this young logician, Kurt Gödel, and he's wrestling with the very idea of proof. He comes up with this wild idea to construct a statement that isn't about numbers or shapes, but about the system of math itself. He creates a sentence that talks about its own ability to be proven.
And here it is. This statement cannot be proved. That's it. Just 5 simple words. But inside that sentence is a paradox that would change mathematics forever. So let that sink in for a second and ask yourself, is that sentence true or is it false?
All right, let's walk through this mind-bender together. Option 1, the statement is true. Well, if it's true, then it's telling the truth, which means it cannot be proved. Whoa. So we have a true statement that our system of math can never actually prove. Okay, what about option 2? What if the statement is false?
Well, if it's false, then its claim that it cannot be proved must be wrong, which means it can be proved. But wait a minute, a consistent logical system can't prove something that's false. That's a complete contradiction. So the only way out of this logical trap is that the statement has to be true and also unprovable.
And this leads to the absolutely staggering conclusion. What Gödel proved is that any logical system, as long as it's powerful enough to do basic arithmetic, will always have a hole in it, a blind spot. There will always be true statements that are just beyond its reach. The system is fundamentally and forever incomplete. And just like that, the dream of a perfect, all-knowing mathematical system was over.
So what's the big takeaway here? Well, it means you can never build a machine, an ultimate computer, that can solve every single mathematical problem. It's just not possible. Gödel's theorem proves that math isn't just a mechanical game of shuffling symbols and following rules. It demands leaps of intuition, flashes of creativity, and deep insight, things that, for now at least, seem to be uniquely human.
So if math isn't this perfect, all-knowing machine, then what is it? Well, in this final part of our journey, we're going to see how mathematicians pivoted. They moved on from that old dream of absolute proof and instead started developing these incredibly powerful new languages, new tools to describe the deep, hidden structures of our universe. We're talking about symmetry and order. And two of these new languages are really, really important: group theory and lattice theory. Think of it like this. Group theory is the mathematics of symmetry. It's all about transformations, like a rotation or a flip, that leaves something looking exactly the same. Lattice theory, on the other hand, is the mathematics of structure and order. It's about hierarchies, about how things fit together and are related.
Let's zoom in on group theory for a second. This is the toolbox that physicists use to understand the fundamental building blocks of the universe. I mean, it's so powerful that it predicted the existence of certain subatomic particles before we ever had the technology to find them. It's also the reason we know that crystals can only form in exactly 230 specific patterns and not a single one more. It's literally the math of hidden rules.
And then there's lattice theory. This is the language we use to talk about pure structure. It doesn't really care about numbers. It just cares about relationships. How are things connected? How are they organized? Think about a family tree, or even the file folders on your computer. That's lattice theory in action. It's absolutely fundamental to modern logic and computer science. It's the architecture of information.
So, let's step back. What is this whole journey, from that dream of perfect sets to fuzzy logic to Gödel's ghost in the machine, all the way to these new theories? What does it all tell us? It points to a huge shift in how we think about math. It's not some rigid, perfect set of rules that was just waiting for us to discover it. It's more like a powerful, flexible set of tools that we, as humans, invented.
And this timeline really lays it all out, doesn't it? We started in the 1880s searching for that perfect, absolute foundation with set theory. Then, boom, 1931, Gödel comes along and shows us that's an impossible dream. So what happens? Well, by the 60s, we get new tools like fuzzy sets to handle the real world's messiness. And that brings us to today, where these amazing languages of symmetry and order are essential for everything from physics to computing. You see, math didn't break, it just grew up. Which brings us to the final and maybe the biggest question of all. If math really is a language that we invented, a set of tools we created, then why is it so unreasonably good at describing the universe? Seriously, why do these abstract ideas we cook up in our minds map so perfectly onto the real world, from the tiniest quantum particles to the vast orbits of galaxies? That deep, beautiful, and kinda spooky mystery, well, that's what keeps us all coming back for more.